The processes that we'll deal with in this course can be fairly complex. Not only could they have multiple input and output streams, but they also may contain internal recycle streams that we need to account for as well. And so, to keep track of all the components in our system and to keep track of all the input and output streams, the main analytical tool that we'll rely on is the material balance. And so to keep track of process inputs and outputs, we're going to use material balances. Balances are used. And I'll typically abbreviate them as MB. Okay? And so the material balance generally just has, it relies on one simple equation. All right? And so with the material balance, what we're going to look at is accumulation in the system. Accumulation of some sort of process variable. Okay? And so accumulation, just by definition, is going to be equal to your final amount minus your initial amount. Okay? So that's one way we can account for accumulation. Another way, but equivalent way, that we could account for accumulation is by looking at, all of the inputs into the process, subtracting off all of the outputs, adding in anything that's generated, so a generation term, and then subtracting off anything that's consumed. Okay? And so this is true generally for open systems. All right? All right, and so one way I'm going to shorten this is by saying A for accumulations equal to input minus output plus generation minus consumption. All right? And so what I wrote here is perhaps not only a fundamental equation in this course, but a fundamental equation in all of chemical and biomedical engineering. Basically, everything you're going to do in your coursework from now on, throughout the rest of your undergraduate career, and even into your professional career, is just going to rely on this simple equation, the material balance equation. And so, to emphasize its importance, what I'm going to say, or what I'm going to command, is that for all your homework assignments, quizzes, and exams, this equation must be written at the beginning. It must be written for all material balance problems. Okay. Right? And I'm not just doing this to give you tedious work, but I'm emphasizing and I'm requiring that you write this equation is because it's a very important tool for analyzing your process. It's an important tool for figuring out what is possible for a given process. For instance, using material balances, you could figure out, what's the theoretical maximum production of a chemical plant. Or, if you're designing a process, some sort of reactor, you could figure out, and you want to hit some sort of target flow rate for your product, you could use a material balance to figure out how much reactant you need to feed into the process. All right? And so you could calculate those things just from doing a simple material balance. And really, a material balance is basically identical to the act of balancing a checkbook. Oh, checkbook. Right? And so with a checkbook, right, you care about how much you're putting in, how much you're spending, and how much interest you're generating. So basically the same things that you deal with when you're dealing with material balances. All right? And so that's just, in general what a material balance is. But of course, there's various types of material balances as well. Just like we have various types of different processes. All right? And so the two classes of material balances that you'll deal with are differential balances. And so these have to deal with anything that involves a rate. And so the key here is to look at units. And so if you're given a flow rate, right, that deals with our process, if you're given a process variable that's given in units of some sort of property per time, that means you're going to have to use differential balances. Okay? Another class of material balance that you'll deal with are integral balances. Okay? So integral balances deal with amounts, or absolute amounts. And so here, you would just, rather than seeing kilograms per second, you would just see kilograms, or pounds, or moles, or something like that. Okay? And so, there's two different types of material balances. But this, if you remember from the previous video, this also tracks with two different classes of processes that we deal with, right? So if you see that you're given a process variable in units of property per time, that means you're going to be dealing with a differential balance. And so that's a key, or that's a hint, that what you're dealing with is a continuous open system. Actually, maybe not even continuous, just an open system. Right? And if you're given just strict amounts, that's a hint that you're dealing with a batch system. So that's just something I want to point out real quick, right? So if you're given, kilograms per time, that means you're likely dealing with a open system. And if you're just given kilograms, you're likely dealing with a batch system. And so for the open systems, that means you're going to be using differential material balances, while with the batch system, you're going to be using integral balances. It's not really going to change much about the math, but it is good to know, have a good understanding of what type of system you're dealing with. All right? In any case, when you're using material balances, some key things to remember are the following. When using MBs, remember these things. So the key thing, the thing that makes material balances work, right? The key concept is that mass is always conserved, right? Right, so if 5 kilograms goes into the process, 5 kilograms needs to be leaving the process, right? So that is true. That mass has to be conserved. But we not only deal with mass in this course, right? We also deal with moles. And the one thing, or one of the main things you need to remember here is that moles may not be conserved if there's a reaction going on. For instance, if you had a reaction in which, 2 moles of reactant becomes 1 mole of product, that means if you fed in, 10 moles into your process and the reaction went to complete conversion, you would only get 5 moles of product, right? And so the number of moles decreases, but at the same time, if you looked at it from a mass basis, the kilogram of reactant going into the process has to be equal to the kilograms of product leaving, right? So those are the two main things that you should always remember, that mass is always conserved, but moles may not be strictly conserved. And so at this point, I want to kind of go over, I talked in general about, what a material balance can do. But I actually want to go over now about, what the material balance looks like for some common processes that you'll encounter in this course. So, MBs of common processes. Okay. The first type of process I'll discuss is a continuous, steady state process in which there's no reaction. Okay? Alright. So let's think about this type of process. And so what we're going to do first, as you should always do, is let's start out with just writing our general material balance equation. So A equals I minus O plus G minus C. Okay? So we should always start with that. Okay? And so with this process, it's continuous. We need to look at the key words here in the process description. So it's continuous, it's steady state, and there's no reaction. And so first thing we should latch on to is the word steady state here. And so if we see that a process is steady state, what that means is that there's going to be no accumulation in the system. Right? And so our A term here is going to be equal to 0. And we could say because it's steady state. Right? So our accumulation term in our material balance is going to go away. The next keywords I'm going to highlight is the no reaction. Right? And so if there's no reaction going on in our system, that means we're not going to have any sort of generation or consumption of a chemical species. And so the G and the C terms are going to go away. All right? And the other thing I'll highlight is the continuous term here. And if you remember from the process video, a continuous process is one in which you have, mass crossing the boundaries of your system. Right? And so that likely means we have some sort of input and output stream in our system. All right, so those are not going to be equal to 0. And so in our material balance, based on the process description, we said that accumulation, generation, and consumption are equal to 0. And so what we're left with is that 0 is equal to input minus output. Or if we rearrange it, we have the input is going to be equal to the output. Right? And so that's what our material balance equation tells us about the process. All right? Let's now move on to, we did a continuous steady state system with no reaction. Let's now think about, sort of the opposite of that. A batch process. A batch process in which there is a reaction going on. Okay? Okay, so once again, we'll start with our general material balance equation. A equals I minus O plus G minus C. And let's break down the process description. All right, and so the first word we have here is we have a batch system. And for a batch process, that means that we have no mass crossing the system boundaries. And so that tells us that we do not have any input or output streams. So I could write batch here. So those input and output are going to be equal to 0. All right? Now, the next term, words that we have here, is with reaction. All right? We don't have any information about the type of reaction, but we do know that there is one going on. So what that tells us is that we likely have some sort of generation or consumption term, depending on whether we're doing a material balance on the reactants or a material balance on the products. In any case, we could just leave the G and the C terms there for right now. Okay? And since we're dealing with a batch process, that means our accumulation term, if we're dealing with a non-trivial batch process, that means our accumulation term is also going to be non-zero. All right? So right now we have A is equal to G minus C. All right? So, we have some information, but we're still not quite, at the point where we could use this tool to, solve for mass amounts. Right? But what we need to remember is if we go back to the previous page, not only did we say accumulation was equal to this equation, but we also said accumulation, just by definition, is a final amount minus an initial amount. And a lot of times when you're dealing with batch process systems, you're either told, the amount of product that you put into the system at the beginning, or the amount of reactants that you put into the system at the beginning, and the amount of products that you take out of the system at the end. All right? And so we could take our material balance equation, where we have A is equal to G minus C, and we could say that's equal to a final amount minus an initial amount. Okay? So we could rearrange this equation to say this, that the initial amount we have in our process plus whatever's generated is going to be equal to the final amount in our process, in our system, plus whatever's consumed. All right? And so from our material balance, we get this sort of relation. And if we know, 3 of the amounts, that could help us figure out what the 4th one is. And so material balances are very useful for, getting a deep understanding about the ins and outs of our processes.